皆さん、はいさい。那覇はいいですね。今日、本当は日本語で話したいですよ。最近勉強していますしね。でも、残念ながら、まだそこ、上手ではないですよ。ということで、英語でお話しします。よろしくお願いします。Thank you very much for having me here. It's a pleasure to be in Naha talking to you all today. I am privileged to be able to talk about a fun little performance regression that we found and fixed in string interpolation during the development of Ruby 3.3. So my name is Matt. I'm 8-Bit Raptor on the internet generally. I am a full-time C Ruby core committer, and I work for Shopify in the Ruby infrastructure team. Now, this talk is related to variable width allocation, which is a feature that my team and I developed to improve the performance of Ruby by changing the way a memory was laid out, and we shipped the first version of this for Ruby 3.2. Now, we continue to work on it during the development cycle for 3.3 to improve the performance and mostly just improve the implementation. And while we were doing this, we noticed a performance regression that we wanted to fix. So I wanted to work out exactly where that regression had come from, and whether it was related to our changes. Now, I'm not going to spend a bunch of time talking about variable width allocation for this talk. We've already covered it at previous RubyKaigis, and it's been in the implementation for a couple of years now. But it is important to understand how Ruby uses memory to understand this talk, so I'm just going to give a quick summary of how allocation works. So when you create a Ruby object, it gets allocated into a specific part of the heap, which is called a size pool, and that's based on the size of the object. The smallest size pool will hold objects that are up to 40 bytes, and then those thresholds double from there. The largest size pool we have is actually 640 bytes, not 320, and anything larger than that gets handled separately. So when we create an object, Ruby chooses an appropriate size pool depending on the total size of that object, and it allocates it. So an object that fits completely within the slots of its respective size pool, we call an embedded object. But objects are malleable. They can be resized after they've been allocated. So for instance, if we substitute out part of this string for something longer using gsub bang, then the receiver object is going to get modified directly. And this will potentially cause it to no longer fit into the size pool in which it was allocated. So in this case, Ruby allocates a chunk of memory elsewhere in the system. Now, it's not particularly important where right now, but it creates a pointer from the original object in the GC heap out to that piece of memory. And now we refer to this object as an extended object rather than an embedded object, because it doesn't fully fit in its slot anymore. And we can inspect the VM-specific information about objects using the objects-based-dump API. And now this is going to show you information about the object size and which pool it's allocated in addition to all the rest of the stuff that it already shows you. So when we run the code like this, we're going to see this output. And this is a bunch of information about that string, its address, whether or not it's frozen, that sort of thing, whether it's write barrier protected and all sorts of stuff. But it's also going to show you the embedded status. This string is embedded, and it's in the 80-byte size pool. And the byte size of the string, which is the amount of memory used to hold the actual string data, is 36 bytes. So given that the string is only 36 bytes, I need to explain why this has been allocated in the 80-byte size pool and not the 40-byte size pool. And that's because every Ruby object gets prefixed with 16 bytes of metadata. This metadata will contain internal status flags about the object, as well as information or a pointer to its class object. And also in Ruby, strings are null terminated, which means we have to add 1 byte for the terminator. And this gives us a total of 53 bytes for this string, making it too big for the 40-byte bucket, and so that 80-byte embedded allocation makes perfect sense. So that's it for our background. At some point when I was working with variable width allocation, I had some code that looked a bit like this. So it allocates a new string, which is built from 2 different strings, a shorter one and a longer one, using string interpolation. And then it inserts that string into a local variable. And I wanted to make sure that these strings were all being allocated in the correct place. So I inspected them using the object space dump API, and this is what I got. So the first string looks good. It's embedded, and it's in the 40-byte bucket, which makes sense as it has a byte size of 5. Remember, 5 plus 16 is 21, plus that null terminator gives us a total size of 22 bytes. The second string also looks good. It's embedded. It's in the 80-byte bucket. Remember, byte size of 29, all the extra stuff gives us 46 bytes. But the third string is not what I expected to see. This new string is the result of the interpolation of the first two strings into a new object. And the byte size of this new string is 36. So when we add the extra header and the terminator, we get a total object size of 53 bytes. So why is it in the 40-byte bucket? And that lack of an embedded flag means that a string has been created as an extended object. So why was this not allocated as an embedded object in the 80-byte bucket? And this is definitely a bug. So I set out to try and find it. And the first thing I did was to look at exactly what the Ruby VM was doing when it executes that code. I ran the code again, but this time dumping out the instructions using dump instructions. And this is going to parse and compile our code, but stop short of actually executing it. Instead, it's going to print out the bytecode to the screen, and we can see exactly what's going on inside the interpreter. So this is a list of instructions that the VM is going to execute sequentially, that is one after the other, just to run that string interpolation code I showed in the previous slide. First, Ruby is going to take our short string, which because it's defined right inside the source code program, it's already been created as an object during the parse and compile phase. So we can take that string and we can push it straight onto the stack. And then we'll use the setLocal instruction, which will pop it straight off the stack and then set it to a local variable, in this case, short str. So then we're going to do the same thing, but with the longer string. We'll take that string directly from the source output, and then we'll set that to a local variable using the setLocal instruction. This next block is what actually performs the interpolation. And finally, the value from that interpolation, again, gets assigned to a local variable using setLocal, and then we're done. Our program exits. We call the leave command, which is going to pop the last remaining object off the stack and return it. So I don't think the actual variable setting code is particularly relevant to this bug. I had a hunch that that was probably all OK. So let's ignore that for now and zoom into the actual interpolation bytecode. I've put the Ruby code at the top of the screen just so we can play along with what's going on. And you can see we have two local variable substitutions inside a string literal. So we start by computing that first substitution. Now, a substitution, you probably know, in a string interpolation can contain any syntactically valid Ruby. But in this case, it's been parsed as a local variable lookup. So the getLocal instruction has been emitted, which looks up that local variable and pushes it onto the stack. And then we call the toS method on it, just to turn it into a string. And after that, we use this any2string instruction. And this is just here to make sure that what we actually push onto the stack is a string. For instance, if toS had been monkey patched to return something that's not a string, then any2string will just brute force it into a string and push it onto the stack. Here on the right, I'm just going to put what the stack looks like at this point in the program. So it contains a single string, hello. And next, we deal with the characters in between those substitution blocks. Again, because those have been defined inside our source code during parsing, they can probably just be pulled out and created as their own separate object. So all we have to do is just put that object as a string and then push it onto the stack. And then we do the same operations that we did for our short string, but for the long string. We grab the value for the local, we coerce it to a string using toS and any2string, and then we push the final result onto the stack. And finally, we use this concat_strings instruction with an argument of 3. And what that's going to do is pull the last 3 items off the stack, 3 strings off the stack, and then it will combine them together into our new string and return it. So seeing as this concat_strings instruction looks to be where most of the actual work is happening, let's go and investigate it. All the valid Ruby VM instructions are defined inside a file in the Ruby source code called insns.def. And this is written using a C-based DSL. And during the compilation stage of the Ruby interpreter, This DSL is going to get processed to generate a C function for every instruction, and then the module containing all of those instruction functions will get included into the VM core, or linked into the VM core. But having them initially in this DSL form gives them some structure that makes them much easier to read and reason about and to work on. So every instruction starts with a call to this define INSNS macro. After that, that's followed directly by the name of the instruction, in this case, concat strings, and then a list of valid parameters and their types. In this case, this instruction takes a single parameter, which is a Ruby numeric type, that is an integer, we call it num. And then we have a list of values that this instruction will pop off the stack. In this case, the ellipsis means that it's variadic. That can be an arbitrary length list. Next, we have the list of values that will be pushed back onto the stack. In this case, a single value object. Now, value just means any valid Ruby type. So we're going to have a value, val, and we're going to push that back onto the stack when this instruction finishes. And then we have some attributes, which I'm going to completely ignore and gloss over because they're not important for my talk. And what follows finally is the actual body of the instruction, everything between those curly braces. And this is the code that's actually going to get executed whenever the VM gets to a concat strings instruction in a bytecode listing. So in this case, it's using our num parameter, which is what was passed in, remember the number 3, and it's going to pass that as an argument to the stack addr from top macro, and that will actually grab the top 3 elements off the stack. It's going to pass those as parameters into a C function, rbstring concat literals, and then the return value of that is going to get assigned to val. Now remember, val is the object that's going to get pushed back onto the stack when this finishes. So essentially, this is pretty simple. Take a pointer to the top 3 stack elements, run some code on them, and then push the return value back onto the stack. So let's go look at the code. This was the rbstring concat literals function. And at first glance, when I looked at this, I saw 2 rough halves to what this function does. The first half, we build a string object that will eventually be our return value for the function. And then the second half, we loop through all of the array of strings that have been passed in, and we append those strings one by one onto that initial string that we defined in the first half. But this first half felt kind of odd to me when I was reading this. It loops through the array of strings that we've passed in as the very first thing it does, and it does that to calculate the size or the total length it needs for the final interpolated string. So it knows up front how much it has to allocate. But then it branches on this magic number, min pre-alloc size, which is hard-coded inside the source code to be 48. And if the length is less than 48, then it falls into the first path of this conditional, where it uses rbstring resurrect, which will eventually set the base string that we're working on to be the first element of the array that we've passed in. However, if the length is longer than 48, then what it's going to do is allocate a completely new empty string using that length that we already know up front. This felt like the right thing to do to me. I don't know why we weren't always doing this. And then when the second half of the function loops through that string array at the top, remember to append onto our string, it starts from either the first or from the second element of the string, depending on which branch we took in that first half of the function. At this point, I was confused. I couldn't explain why we even had to branch at all in this function. What was the purpose of the string resurrection path? What min pre-alloc size was supposed to represent, or what the significance of the number 48 was. But I had spotted the bug. So we have these 3 strings, and the total length of their data is 36 bytes. Now, this is less than the min pre-alloc size of 48, so we're going to go down the string resurrection path. And that means we're going to use our first string as a base. And that string's already been allocated in the 40-byte size pool, so that when we start appending things to it, it's quickly going to push past the boundary of that size pool, which will cause Ruby to convert it to an extended object. And this is how we ended up with that 40-byte extended object rather than the embedded 80-byte object we were expecting. Cool. So we found our bug. Now we have to find out why this code exists and whether it's still important. I broke out the git pickaxe, that is git log -s, and I found the commit that had first introduced this magic number. And it led me to this optimization, which was originally written by Minami Nao and was originally committed by Nobu-san in about 2017 sometime. And the author talks about the use of RB string resurrection, improving performance for smaller strings, and he confirms that yes, minimum pre-alloc size is really just a magic number. It was picked by experimentation on his local laptop back in 2017. And this was like 7 years ago now, so maybe, or 6 years at the time, I guess, when I was developing this. So maybe this optimization isn't really needed anymore. Thankfully, the author had also included benchmarking code inside the commit message, which I duly pull out and ran. And then I ripped out the entire optimization so that I did what I thought the function should be doing, which was always pre-allocate a string of the correct size. And I ran the benchmarks again. And I'd slowed down short string interpolation by 9% nearly doing that. So it looked to me like that optimization was still relevant. It was still doing good work. But it was super frustrating that it just wasn't allocating the strings in the right place. So the first thing I did was to try and fix the bug, but within the scope of the original optimization. I changed that conditional so that instead of taking the optimized path if the strings are shorter than some arbitrary length, what I did instead was take the optimized path only if the final string that we ended up with would still fit within the same size pool. And that would allow us to avoid the allocation penalty that comes from converting an embedded string to an extended one. And I ran the benchmarks again, and this time the performance numbers were much, much closer. There was still some small variance, but nowhere near that 9% performance drop that we saw by removing the benchmark entirely. And these smaller regressions could probably be explained away due to benchmarking noise. The original author was running the benchmarks in a non-controlled environment on his local laptop in 2017. I was doing the same in 2023. And I had also made a subtle change to that particular condition, which could explain this away. But at least our code is correct. The string is embedded. It's in the correct size pool. So our bug is fixed with only a tiny performance regression that's probably OK. So time to ship it, right? Well, I didn't want to rush ahead. I still had this question I wanted to answer, which was why can't I just allocate this in the correct size pool up front? Why does that use of RB string resurrect cause a 9% performance improvement when used on arbitrarily small strings? So despite fixing the bug, I wasn't satisfied with the conclusion. Especially as on closer inspection, RB string resurrect duplicates the string anyway, which does an allocation. So my original hypothesis that it was allocation that was responsible for the slowdown was wrong. So I took a closer look at the allocation path, and I noticed that it seems to be doing some extra work that the string resurrection path is not doing. And that is that once the new string is allocated, we then copy the encoding from the string at the head of the array into this new empty string that we've just created. And to do that, we're using a public API function, RB-enc-copy, and this is from Ruby C API. And now, because this is public, it can be used from C extensions, which means that effectively this function has to deal with user input. It cannot make assumptions about the validity of its parameters at all. And to that end, it does a lot of safety checks on the string that's being passed in. Things like checking whether the string is frozen, the encoding index is in the correct range, or that the terminator lengths are the same. So I benchmarked that code again, but I changed the code to just hard code the encoding, so I didn't want to have to do any of that encoding code, and I ran the benchmarks again on my small setup. And it turns out that this function was exactly our problem. The string encoding was causing this slowdown. The string resurrection code skips all of these safety checks when it sets up the encoding of the duplicated string because it knows exactly what it's duplicating from and into, because this is an internal-only function that can't be used from outside of like CRuby's main code base. But this is also an internal function that can only be used in this one particular place. So this doesn't really need those safety checks either. Because once we've set up our target string, and we've moved into our loop appending into the new string, in most cases, we just overwrite the encoding of the string anyway with what's coming from the array that's being passed in. And as the strings that we're looping through have already been pre-processed, remember we call 2s and then any to string on them to force them to be valid strings, we can be confident that they've passed all these safety checks and they are valid strings. And additionally, our destination, we can also confirm it's a valid string. It's a known quantity. We literally just allocated it in this function. So we can also afford to be less strict with our safety checks here. We need to find an alternative to using this public API function. So I went to research about this public API function and see if any alternatives existed. And I found that serendipitously, Peter, my colleague at Shopify, had run into a case where these safety checks had impacted performance of other string functions, and this was just a few days prior to when I was actually doing this work. And Peter's solution was to introduce a private function, rb_str_enc_copy_direct. And this sets up the encoding, but skips all those safety checks that are part of the public API, so it's much, much faster. So I tried this refactor again. I ripped out the entire conditional so that we always pre-allocate. We get rid of our magic number, we get rid of our branch. And this time I used Peter's less safe but faster internal API to set the encoding. And I don't know about you, but I personally like this code a lot better now. I've reduced the complexity, we've removed some branches, we've removed a magic number, and this just doesn't have that two-part phase that the original code had. We're just simply creating a new string, and then we're combining some other strings into it. And this does fix the original bug. Because we've created that new string from scratch as an empty string, they're all going to be embedded in the correct bucket now. But is it performant? Does it properly solve all of our performance concerns as well as the actual bug? So I took the original benchmarks that I was working with from this commit, and I integrated them into the C-Ruby benchmarking suite, just to make them more repeatable and consistent, and so that we can just run them to try and prevent regressions like this in the future. And when we compared the new patch with the original code, we saw that we doubled the performance of interpolations within that same bucket and improved the performance of interpolations that cross a bucket. And this is a fantastic result. This made me really happy because essentially I just removed 8 lines of code. And so these improvements, yeah, we shipped this. This is what made its way into Ruby 3.3. And now string interpolation is a lot faster and cleaner than it was before. So I hope you enjoyed that story. I would love to tell you that I have some groundbreaking conclusions to share with you all, but I don't really. This was basically just a debugging war story that I had a lot of fun with. But that being said, I would still like to leave you with a few thoughts and followed by a big thank you. The first is that small changes can often have really big impacts, and this applies to our little patch certainly. I was not expecting the removal of 8 lines of code to result in a nearly 2x speed up in some certain cases. But the real message here is that any change can have unexpected impacts. When we'd initially merged the variable width allocation work, we hadn't anticipated running into a bug in a 7-year-old optimization that would be responsible for such a lot of work, and that removing that would have such a huge impact on the performance of string interpolations generally. But unexpected impacts like this are not something that can necessarily be mitigated. Instead, we should be treating them as a learning opportunity. And so I'd like to give you some unsolicited advice, which is always question your assumptions. It would have been very easy for me to have stopped at that first stage here, simply assuming that because I'd already seen the massive performance jump in the optimization path, that it was absolutely still relevant, and that all I needed to do was to make the smallest change in order to fix my specific bug. And I could have just merged that first piece of work. But at this point, I still didn't have an answer to that question, which was, why can't we just allocate the correct size string up front? And I'm quite a stubborn person, which leads me to my next point, which is, don't be afraid to dig into things that you don't understand yet or can't explain. So follow your curiosity and see where it leads. I probably would have stopped at that first change if I didn't have that burning desire to answer that question of why couldn't we just allocate the right size string. And it turns out that with a bit more investigation, we can just allocate the correct size string up front. And all it took was for somebody to think about things in a slightly different way to the original author of that original optimization 7 years ago and be working in a different kind of space. And this diversity of thought is really valuable. The more people with inquiring minds who are questioning assumptions and diving into things they don't understand will result in much more opportunities for real positive changes in the Ruby language and in all of our work going forward. And so that's like my main takeaway messages. The last thing I want to do is to say thank you very, very much to Minami now and to Nobu for working on this PR, this original PR. The commit message particularly was absolutely fantastic. And thank you to Nobu for preserving that commit message instead of just squashing it and pushing something up and merging that into mainline Ruby. This change that I made would have been an awful lot harder and more arduous were it not for those detailed notes. Minami-san summarized exactly why the change was important, what he was intending to do, what he was trying to achieve, and most importantly, included code and benchmarks for how he verified and measured that it was working and doing what he expected. And as someone like me who's coming into this for the first time 7 years later, and I didn't know anything. This was possibly one of the first times I'd worked on string interpolation. I've only been a Ruby committer for a year. And someone trying to decipher why it was behaving oddly, this documentation was worth its weight in gold. So what I'm trying to say really is working on Ruby is an absolute ton of fun, and it can teach you an awful lot. And I would really encourage anyone in the audience who hasn't tried contributing to Ruby before to just go out there and explore the code base and experiment and learn and document stuff that you see. And above all else, have fun. And that's all I've got. Thank you very much for listening.